It's been a long road, and now we have covered different building blocks of a data flow pipeline, like being basic concepts, windows, watermarks, and triggers, and their usage in creating data processing pipelines, along with different sources and sinks supported in Dataflow. This optional video will be taking a deep dive into schema, what they are, how to create and insert them, how to transform schemas, and how to work around Python's limitations in Beam in regard to schema transformation. So let's get started. A P collection must consist of elements of the same type. To Beam, these collections of types are blocks that are passed between transforms. Often, the types of these records being processed have an obvious structure. Common Beam sources produce JSON, Avro, protocol buffer, or database row objects. All of these types have well-defined structures that can often be determined by examining the type. By understanding the structure of a pipeline record, we can provide much more concise APIs for data processing. Most structural records share some common characteristics. They can be subdivided into separate named fields. Fields usually have a string name, but sometimes, as in the case of indexed tuples, have numerical indices instead. There is a confined list of primitive types that a field can have. These often match primitive types in most programming languages, like integer, long, string, etc. Often a field type can be marked as optional, sometimes referred to as nullable or required. For example, when using Avro.io to read Avro files, the source can automatically infer a Beam schema from the average schema and attach that to Beam P collection. Often records have a nested structure. A nested structure occurs when a field itself has two fields. So the type of the field itself has a schema. These structured records have some commonly feature array or map type fields. Now, in order to take advantage of schemas, your P collection must have a schema attached to it. Often the source itself will attach a schema to the P collection. For example, when using an Avro.io to read files, the source can automatically infer a Beam schema from the average schema and attach that to the Beam P collection. In the following example below, consider the following schema, representing actions in a fictitious e-commerce company. Purchase event records are represented by the above purchase schema. Each purchase event contains a shipping address, which is a nested row containing its own schema. Each purchase also contains an array of credit card transactions, a list because a purchase might be split across multiple credit cards. Each item in the transaction list is a row with its own schema. In Python, you can use the following set of classes to represent the purchase schema. Beam will automatically infer the correct schema based on the members of that class. Let's take the purchasing class, for instance. It has 5 fields: the user ID, the item ID, the shipping address, the cost and cents, and the transactions. The schema for a P collection defines elements of that P collection as an ordered list of name fields. Each field has a name, a data type, and possibly a set of user options. A field can also reference a nested schema. In this case, the field will have type row, and the nested schema will be an attribute of the field type. 3 collection types are supported as field types: array, iterable, and map. Now, an array, this represents a repeated value type, where the repeated elements can have any supported type. Arrays of nested rows are supported, as are arrays of arrays. Now, an iterable, this is very similar to the array type. It represents a repeated value, but one in which the full list of items is not known until the iterate is over. This is intended for the case where an iterable might be larger than the available memory and backed by external storage. For example, this can happen with the iterable returned by a group by key. The repeated elements can have any supported type. Map. This represents an associative map from keys to values. All schema types are supported for both keys and values. Values that contain map types cannot be used as keys in any grouping operation. Now let's look at an example of creating a schema, and this is the named tuple class. The named tuple class is a Python class that wraps a tuple, assigning a name to each element and restricting it to a particular type. Beam will automatically infer the schema for P collections with named tuple output types. There are also methods for creating ad hoc schema declarations. First, you can use a lambda that returns instances of beam.row. Feel free to pause the video at any time if you need to write any of this code down. Sometimes it can be more concise to express the same logic with the select transform. Note that the declaration doesn't include any specific information about the type of the bank and purchase amount fields, so Beam will attempt to infer the type information, which is actually what we have just gone over. Now let's say that Beam is unable to infer the type information, then it will fall back to the generic type of any. Sometimes this is not ideal. You can use cast to make sure Beam correctly infers types with beam.row or with select. Let's look at aggregations group by. The names of the key and value fields in the output schema can be controlled using with key field and with value field builders as follows. It is quite common to apply one or more aggregations in the grouped result. Each aggregation can specify one or more fields to aggregate, an aggregation function, and the name of the resulting field in the output schema. For example, the following application computes 3 aggregations grouped by the user ID, with all aggregations represented in a single output schema. The group by transform allows simply grouping data by any number of fields in the input schema, applying aggregations to those groupings, and storing the results of those aggregations in a new schema field. The output of the group by transform has a schema with one field corresponding to each aggregation performed. The simplest usage of group by specifies no aggregations, in which case all inputs matching the provided set of fields are grouped together into an iterable field. The key field contains the grouping key, and the value field contains a list of all the values that matched that key. Beam unfortunately is very limited in their Python schema transforms and must use SQL APIs or data frame APIs. In this example, we're reading from BigQuery using their I/O module, which we learned about in the last lesson. Some of these examples have already been shown, but I'm circling back to the BigQuery module because most schema transforms are not set up for Python, and BigQuery is a workaround to that problem. This example shows how to read from an entire BigQuery table. Use the table parameter with the BigQuery table name. This is another example that we've already been over. But as a refresher, if you don't want to read an entire table, you can supply a query string to read from BigQuery by specifying the query parameter. The following code uses an SQL query to only read the max temperature column. All right, let's look at the BigQuery filter transform. Now this is a really long example and I'm not going to go through it line by line because we've already done that. We've already covered what the code looks like line by line, and at this point we shouldn't need those type of training wheels. So in this example, we're selecting the item numbers, store numbers, bottles sold, and the state bottle retail from our BigQuery table using a query string. Then we're filtering using side inputs to the filter transform. Writing to BigQuery, create disposition. The create disposition controls whether or not your BigQuery write operation should create a table if the destination table does not exist. Use the create disposition parameter to specify the create disposition. Valid enum values are BigQuery disposition, write.create if needed. Specifies that the write operation should create a new table if one does not exist. If you use this value, you must provide a table schema. Create if needed is the default behavior. BigQuery disposition.create never specifies that a table should never be created. If the destination table does not exist, the write operation fails. If you specify create if needed as the create disposition and you don't supply a table schema, the transform might fail at runtime if the destination table does not exist. The write disposition controls how your BigQuery write operation applies to an existing table. Use the write disposition parameter to specify the write disposition. Valid enum values are BigQuery disposition write empty specifies that the write operation should fail at runtime if the destination table is not empty. Write empty is the default behavior. BigQuery disposition.write trunket specifies that the write operation should replace an existing table. Any existing rows in the destination table are removed, and the new rows are added to the table. BigQuery disposition.write append specifies the write operation should append the rows to the end of the existing table. Continuing on with writing to BigQuery, let's look at table reference. This transform allows you to provide static project, dataset, and table parameters which point to a specific BigQuery table to be created. The table parameter can also be a dynamic parameter or callable, which receives an element to be written to BigQuery and returns the table that the element should be sent to. You may also provide a tuple of pCollection view elements to be passed as side inputs to your callable. In this example, we're sending events of different types to different tables, and the table names are computed at the pipeline runtime. If your BigQuery write operation creates a new table, you must provide schema information. The schema contains information about each field in the table. When updating a pipeline with a new schema, the existing schema fields must stay in the same order, or the pipeline will break, failing to write to BigQuery. To create a table schema in Python, you can either use a table schema object or use a string that defines a list of fields. Single string based schemas do not support nested fields, repeated fields, or specifying a BigQuery node for fields. The mode is always set to nullable. To create and use a table schema as a table schema object, follow these steps. First, you're going to create a table schema object. Then you're going to create and append a table field schema object for each field in your table. Then you're going to use a schema parameter to provide your table schema. When you apply a write transform, set the parameter's value to the table schema object. The following example code shows how to create a table schema for a table with two fields, source and quote, of type string. So now let's look at creating a table schema as a string. To create and use a table schema as a string, follow these steps. Create a single comma separated string in the form field 1, type 1, field 2, type 2, field 3, type 3 that defines a list of fields. The type should specify the field's BigQuery type. Step 2. Use the schema parameter to provide your table schema when you apply a write transform. Set your parameter's value to the string. The following example shows how to use a string to specify the same table schema as the previous example. Continuing on with writing to BigQuery and schema, this transform also allows you to provide a static or callable schema. In providing a callable, this should take in a table reference as returned by the table parameter and return the corresponding schema for that table. This allows you to provide different schemas for different tables. Let's continue to look at the write to BigQuery transform. This sync is able to create tables in BigQuery if they don't already exist. It also relies on creating temporary tables when performing file loads. The write to BigQuery transform creates tables using the BigQuery API by inserting a load job or by inserting a new table. When creating a new BigQuery table, there are a number of extra parameters that one may need to specify. For example, clustering, partitioning, data encoding, etc. And all of that, we're going to get into that when we get to BigQuery. It is possible to provide these additional parameters by passing a Python dictionary as additional BigQuery parameters to the transform. Here's an example of creating a table that has specific partitioning and clustering properties. Much like the schema case, the parameter with additional BQ parameters can also take a callable that receives a table reference. So let's summarize. A schema describes a type in terms of fields and values. Each field is named and has a type. Schemas can be nested arbitrarily and can contain repeated or complex fields as well. When you use a schema in Dataflow jobs, you make your code more readable and easier to manage. Also, it allows the Dataflow service to make optimizations behind the scenes as it is aware of the type and the structure of data being processed. For example, the Dataflow service optimizes the encoder and decoder required for serialization and deserialization of data as it moves from one phase to another. That's going to wrap up this section on schemas. I hope it was very helpful. That's going to wrap up this optional lesson on schemas, which is video 5 in the Dataflow for Google's Data Engineering Certification Series. Good luck out there, and hopefully you'll follow along with the rest of my lessons on Google products, specifically centered on both test questions and the implementation of Apache Beam.